to them. The spore colonies were being used to terraform the planet. So these are the spores. You can ignore the text now because I'm just showing it, and there was other text there that I couldn't quite get rid of. So they have floating spore colonies up there that are apparently doing something to the atmosphere to make it nice and breathable. That's good. I like breathing. So here's another shot of them, and they have these little things floating down, and it causes bad things that are important to the plot line that I obviously don't care about. So that's the idea, but what's wrong with that? Well, when I first was doing this panel on Sunday mornings, I would try to get people to wake up by having audience participation, and whenever I would propose one of these questions, I'd always go, is that plausible, and have everyone say, no, what idiot thought that up? Well, this is the guy that thought this up. I can tell who's over the age of 20 in here. This, for those of you that don't know, is Carl Sagan. He is one of the most famous popularizers of science back in the 70s and 80s because he had a series of documentaries called The Cosmos where he brought the public eye to astronomy and just did some fantastic lessons on basic astronomy that actually still work out really well today. I was watching them last month, and there's very little that's changed since then. So he was very, very famous, but before he became a popularizer of astronomy, he was an actual scientist. And in a 1968 paper, he wrote one on the planet Venus. It was about 70 pages long, and in it he said, after the physical environment has been thoroughly investigated, and if indeed Venus proves to be without life, there will exist the prospect of microbiological planetary engineering. Did we catch all that? All right, so here's what it was proposing. He says, an organism is needed which can photosynthesize in the high atmosphere of Venus according to the symbolic equation CO2 plus H2O plus light is turned into CH2O plus O2. The oxygen arising from the water. In time, the organisms will be carried to lower atmospheric levels where, because of the higher temperatures, they will be roasted, decomposing ideally, according to the symbolic equation, CH2O plus heat turns back into carbon plus H2O. So the idea of this is you toss some kind of spore thingy up in the atmosphere, it takes the CO2, which is in the atmosphere of Venus, takes the carbon out of it through photosynthesis. Because it absorbs the carbon, it becomes heavier, it falls down to lower levels, and if you don't know, the surface of Venus is hot enough to stick a plate of cookies out the window and bake them. So it would get very roasted, and when it breaks down, it would re-release the carbon and break the H2O back apart. The H2O would vaporize, go back up into the atmosphere, and start the process over. And this would remove the CO2 from the atmosphere and leave free O2. Cool idea. One problem. Where's the hydrogen? If none of you have ever played with hydrogen gas before, it's lighter than helium. It would tend to float away. That's why we don't find it in atmospheres. So if you don't have it being bound up very quickly in H2O or something, you don't have it available. Eventually, Carl Sagan realized this and wrote another paper later going, oopsie, I made a mistake. This was written before any of the probes were sent to Venus to know what the atmosphere was like, but eventually he corrected the mistake. Cowboy Bebop didn't. So they did well at the beginning and then dropped the ball. Another one from Cowboy Bebop was the Heavy Metal Queen episode where Spike is trapped in an asteroid of some sort and they can't get out, so he sends his little pod capsule full of explosives to go blow up the wall and get him out. And to kind of get himself so he doesn't get blown up, he jumps out of his ship into another. So here's a clip showing that. So he's going to say he's going to do his floating act. He just plugs his ears, takes a deep breath, pops the hatch into a perfect vacuum. Yeah, that was smart. Alright, so what's wrong with that? Well, it turns out back in the day of the Apollo missions, they were trying to figure out what would happen if they actually did have some sort of catastrophic failure. So this huge paper was commissioned called the, I'll get to it in a minute, it's printed down at the bottom, but it's basically 200 pages of nasty. All the horrible things that can happen to you if something goes wrong. There's two main ways it's going to hurt you. The first is just the explosive decompression, which is going from a nice normal atmospheric pressure to a hard vacuum. And the second one is what's going to happen if you stay in that vacuum condition very long. If you kind of see how this is set up, there were going to be two columns. I was going to kind of list them for each, but they overlap so much that I just decided to list them. First off, hypoxia. You can't breathe. You're not going to get oxygen, so you're going to have a lack of oxygen in your blood, which will cause you to have cyanosis. You will turn blue. You also get decompression sickness, which is also known as the bends, which is where the nitrogen in your blood comes out of solution and you get nitrogen bubbles forming in your blood, which can get to your heart, brain, cause strokes, and all sorts of other wonderful things that you don't want. Obviously, other bad things can happen. You can have short and long-term central nervous system damage. That doesn't sound pleasant. On top of it all, you might feel a bit nauseous. And because you have things that were formerly dissolved turning into a gas, you might feel a bit bloated. In other words, you're going to swell up, which can rupture pulmonary tissue, also sinus and eardrums, and it might cause some severe abdominal pain. In that episode, he had about 60 seconds in which he jumped from one ship to the other, and he was perfectly fine the whole time. He didn't black out or anything, but in reality, you get to 5 to 15 seconds of what's called useful consciousness. This is where you can still function and think at all, and after that, people that have had things like this happen describe it as being very drunk for about 3 seconds, and then they don't remember anything. So it's not something you'd exactly want. But let's figure out exactly how bad this is. Also from that paper, they had done a whole bunch of tests on cute little fuzzy animals. Don't tell PETA. They did it on rats and rabbits and other things that start with R. But the things I want you to see is they have a large change in the pressure. You start off and your atmospheric pressure goes something really low. But the way we can really look at this is look at it first on how quickly they do it. About 0.6 of a second to 1/1000th of a second. And you see that as they do that, the mortality rate goes from 0 to 100. That means you do it too quick, you're going to die. The question is, where is Spike on this graph? So here's a graph that shows the area of the orifice that the air is going to be leaking out of versus the volume of air. And if you approximate Spike's little capsule as a nice perfect sphere and ignore some of the equipment he has in there just to make the math simple, it turns out he is right about there. Which means the air will be leaking out between 0.01 seconds and 0.001 seconds. This is a logarithmic graph, so it's actually much closer to this than it actually looks. So you can figure out exactly where that is, put it back onto the last graph, and he is down here. If you graph that one up and put the time in, it turns out it's an actually 83% chance of mortality. I would not want to take that chance. I would rather play Russian roulette. I think Spike's an idiot. So, that is... So now I get to go into all the new stuff that I prepared for just this year. Each time I prepare this panel, it takes me generally about 100 hours worth of work to do it. This is my second biggest hobby, only second to World of Warcraft. Yeah, you can tell where this ranks for me. I have 3 new segments this year, and to start off with the new ones, this is the most requested thing I've ever gotten. How the hell does a Pokeball work? I didn't want to touch this for a long time because, well, I've seen so many rationalizations and there's different ways it's supposed to work depending on the manga or the TV show, and finally I just decided, you know, I'm going to pick one way, use one way to constrain my variables, and just hope that I don't have anyone that nitpicks too much. So, first off, what is a Pokeball? Well, it does something to the Pokemon where it makes them go all glowy. And then they turn into this little beamy thing, and then they go inside it. That's what she said. So, there's 2 things that seem to happen. First off, the Pokemon no longer has a cohesive form. He's not all together. He was somehow disassembled at the very least. Kind of like a Star Trek transporter, maybe? So, who knows, but at least for the Star Trek transporter, you end up somewhere else whole. Pokeballs are kind of too small for that, so maybe they just kind of broke them down into a pile of atoms that are sitting there, and they'll release it later and put it back together somehow. But if that were the case, then you would still have conservation of mass, and I don't see Ash carrying around a 500-pound Pokeball with an Onyx in it.